Okay. Do you have the pointer? Oh, it's here. Thank you. So good morning, everybody. Compared to the two previous talks, what I have to say will seem rather trivial. Actually, it's the introduction to a research project, polar duality and quantum mechanics I'm conducting at the University of Vienna. So what is it about? All right. Let me first see how this works here.
Faut utiliser les flèches de l'ordi.
Ah bon, les flèches, mais lesquelles?
Non, sur l'ordinateur.
Ah d'accord, ok, bon, ah yes, okay. So first, a few references. The first is the one which has appeared in the preceding volumes. And what I'm going to say today is actually a slight improvement of this. And then there are a few other papers where I introduced the idea of polar duality in quantum mechanics. Well, okay, so here some mathematical setup. Okay, so I will be working in a phase space.
Parlez dans le micro parce qu'on enregistre.
I will be working in the phase space R2n, which I identify with the product of the configuration space and the momentum space. Then, okay, I'm using the standard symplectic form, which is written in differential notations like that, or in matrix notation using the standard symplectic matrix. Then the symplectic group SPN is a well-known object of force in symplectic geometry. Nothing to say about that. And then the Lagrangian-Grassmannian, just so perhaps everybody is not so familiar with the Lagrangian-Grassmannian. Well, it consists of all Lagrangian planes in a symplectic phase space. Lagrangian planes are maximal co-isotropic subspaces. That is, they are subspaces of dimension n on which the symplectic form varies identically. It can be identified topologically with two homogeneous spaces, U and C, the unitary group divided by the orthogonal group, or with WNC. So what is WNC? It's the set of all symmetric unitary matrices. This identification is very important in practice. It was actually discovered by Soyo in a note au compte rendu de l'Académie des Sciences. But I'm not going into the details here because, okay, they are not necessary. A very important thing is that the symplectic group acts transitively on the Lagrangian-Grassmannian. And actually, the unitary group UN also acts transitively on it, but this is less important in our context here. Fine. So, okay, I define the notion of Lagrangian frame. A Lagrangian frame is just a pair of transverse Lagrangian planes. The transverse, it means that their intersection is zero, or equivalently that the whole phase space is the direct sum of L and L prime. The basic example is if you take the coordinate planes, Lx and Lp, then they form the so-called canonical Lagrangian frame. A very important thing is that the symplectic group acts transitively on the set of all Lagrangian frames. It means that if you have a Lagrangian frame and another one, you can always transform the first one into the other using a symplectic transformation. This is a very basic property. It's not very difficult to prove, actually using basis. It's false, for instance, that the unitary group should act on the set of Lagrangian frames, because there you have then questions of angles which intervene. Good. This being said, I introduced the notion of polar duality. It's a notion from convex geometry. Okay. You define the polar dual of a convex set X in this way here, the supremum of the products Px for all x in X, smaller or equal to h bar. Actually, h bar is taken equal to 1 in the usual theory of convex geometry, but since we are going to quantize this, I prefer to introduce a parameter. Well, it's of course very easy here. The basic properties of polarity are those here. Here it's reflexive, it's anti-monotone, and then we have a scaling property also. Okay. In particular, if we multiply the set X by a constant lambda, then you have to divide the polar dual by this constant lambda. Basic example here, if you take the ball with radius square root of h bar in X space, if you take its polar dual, you get the same ball, but then in momentum space. So this is a fundamental duality property here. More generally, if you take an ellipsoid ax squared smaller or equal to h bar, then you take the polar dual by just inverting the matrix. It's related to the Legendre transform, but I will not have time to explain this more in detail. Good, so now Lagrangian polar duality. It's a variant of the usual notion of polar duality. I take a Lagrangian frame, I take an ellipsoid XL supported by L. I suppose that this ellipsoid is centered at the origin, and then I define XL L prime H bar, that is its polar dual with respect to L prime, by this formula here. You see, the symplectic form intervenes here. And this is fundamental because thanks to the transitivity of the action of the symplectic group on the set of frames, this makes sense and can be adapted to define geometric quantum states. Note that the fact that XL is centrally symmetric is very important. And I will make a few remarks about that at the end of the talk, because if you don't take centrally symmetric sets, you will have to use what is called the Saint-Malo point, and it leads to difficulties. So this is why what I'm doing here is rather trivial, because we don't have any geometric difficulties. So this being said, what is a geometric quantum state? So I call geometric quantum state the datum of Cartesian products of one convex set XL by its polar dual. So it's a subset of the product of two Lagrangian planes here. Yes, it's the Lagrangian, the geometric state associated with the frame L prime, and I denote by quant 0n the set of all such that geometric states here. So this might seem very abstract, but the point is that this is in relation with the set of all Gaussians. See why here. So first, a basic example. If I take for XL the ball with square root of, with radius square root of h bar in X space, then the quantum state is just the product of these two balls here. Now, essential remark is that the John ellipsoid of this state here is actually the ball with radius square root of h bar in phase space. What is the John ellipsoid? Well, I think that we're more or less familiar with that. If you take a convex set or a convex body here, John ellipsoid is the ellipsoid with maximal volume contained inside it. For instance, if you take a square, it's the circle which is inscribed in it, and so on. And this is in opposition to the so-called Löwner ellipsoid, which is the minimum volume ellipsoid containing a set. So here we're talking about John ellipsoids, and why are we doing this? Because here we have a symplectic action of the symplectic group on quant n here. It's trivially defined. Actually, you have to work to show that it's really an action. You have to work a little bit, but the important point is that it is transitive. So given two geometric quantum states, you can pass from the first to the second using a linear symplectic transformation. And of course here, what happens also is that because of the transitivity, is that every geometric quantum state can be obtained from the canonical one using a symplectic transformation here. So this means also that the John ellipsoid, of course, of an arbitrary state is S applied to the ball with radius square root of h bar in phase space. And these balls, or the images of these balls by symplectic transformation, play a central role in quantum mechanics under the name of quantum blobs. It's a terminology I introduced several years ago. They represent minimal volume and minimal symplectic capacity units compatible with the uncertainty principle. Well, the proof of this is rather elementary. Well, there's a little work to do, but not so much. Then, okay, relation with Gaussian quantum states. Okay, here, what I denote here, psi gamma AB, is a not a standard Gaussian, but what is called a generalized Gaussian or a multi-correlated Gaussian in physics. The exponential factor I gamma is in fact irrelevant. It's just multiplication by a complex number with modulus 1. And then you have normalizing factors there. So the L2 norm of that is equal to 1 here. A is positive definite, B is symmetric, and if you take A equal to the identity and B equal to 0, you recover the usual standard Gaussian state here. Now, the very important thing here is that if you calculate the Wigner function, the Wigner transform of these Gaussian states, it's given by this formula there, where S is, okay, I did right here, yeah, S is the S defined here. It's not trivial, but it's well known. So, and it actually can be proved by using the properties of the metaplectic group. You know, the metaplectic group is the unitary representation of the double cover of the symplectic group, and doing some manipulations and calculations which are not particularly difficult, you can prove this formula here. Fine, so the main result, or rather the first main result, is that we have a bijection between the quantum states. The L is just to remind that they are elliptic here, onto the Gaussian defined by this formula here. This is a bijection here. That is, this theorem identifies my abstract geometric quantum states with Gaussians here. Actually, it does a little bit more, because, okay, I say that on next slide. I'll tell you why I say a little bit more here. It has to do with covariance ellipsoids here, actually. So, where S hat in NPN is the metaplectic group, covers the S such that the geometric state is obtained from the canonical one using a symplectic transform here. The covariance matrix of S hat phi 0 is given by H bar over 2 SST. This will be valid as well in a more general setup, as I will show next. The proof of this is based on a very simple idea. The main difficulty is to prove that S hat phi 0 does not depend on the choice of S. Okay, let's suppose that S prime is also another symplectic matrix satisfying the formula there. Then S prime must be equal to SU, where U is a rotation or an orthogonal symplectic matrix here. And it follows by rotational symmetry that S prime hat phi 0 is the same thing as S hat phi 0. Using the same idea, then you show that the mapping is surjective and injective, so you get a bijection here. Now, the last result which generalizes this here. Okay, I can define the notion of mixed state here. The geometric states I was talking about here were actually pure states. That shows the identification with pure Gaussian states here. But you can define a more general notion here by taking a Lagrangian frame, XL in L be an ellipsoid with center 0. A mixed geometric state is the product XL PL prime, where PL is a centered ellipsoid containing the polar dual XL HL prime here. So the theorem, previous theorem extends as follows. If the mapping mu, which to XL PL prime associates the mixed Gaussian state with Wigner distribution rho z here, is also a bijection. And actually, what this means is that you can go beyond Gaussian states here. You can see XL, these geometric states XL, PL prime, as representing covariance matrices for arbitrary quantum mixed states here. That we then can choose in particular a Gaussian. Okay, that's just an illustration, but you have infinitely many mixed states having the same covariance matrix or equivalently to the same covariance ellipsoid here. Okay, yes, one thing here to remember here is that not every matrix sigma is a quantum covariance matrix. It must satisfy a condition here, which is sigma plus I over h bar j, positive semi-definite. But this is equivalent to the fact that the corresponding ellipsoid contains a quantum blob that is the image of the ball with radius square root of h bar by a symplectic transformation. But all these details are rather technical, and it's not in a short talk. Of course, I will have time to explain that. So, okay, this was what I had to say with a broken voice, and apologize if I wasn't quite clear.
So, is there any question for the speaker?
I noticed there is some similarity with the theory of Helmholtz about pairs of subspaces in general position, and then consecutively the theory by Van Dalen and Marsden making the link with Tomita Takezaki theory.
Okay, I was not aware of that. Do they?
So we can discuss that.
Yes, you mean that Paul Helmholtz had...
I'm sorry?
Paul Helmholtz had already...
Yeah, sure.
That kind
100
of
years
thing.
ago, maybe.
This is interesting. I would like to discuss that with you. Then I wasn't aware of that, no?
Yeah, thank you very much. Very inspiring talk. I like the idea of that bijection, and I noticed you said already something about how this relates to general wave functions. For me, it's still not clear how do you relate these correlation matrices in general to an arbitrary L2, say, wave function. Is there like a mapping, or how can I see the relation in more detail, basically?
This is work in progress. Actually, as soon as you take other convex sets than ellipsoids, you have difficulties. Because first, especially if they are in general position, because first of all, to define polarity, you cannot use the center of mass. You must use something else, which is called the Santalot point. And this leads to quite difficult constructions. There are many other constructions. Let me just say that this is related, although it's not visible, to the Mahler conjecture, as it's called. You know, the Mahler conjecture says that the product of the volume of a convex body X and that of its polar dual have a lower bound, which is very precise, but nobody has yet been able to prove that. So you have many difficult things which appear in this context here. So this is just a sketch of the beginning of the preamble to a project.
Maybe just one additional thing is, I mean, there are basis sets for L2 functions beyond. I mean, Gaussians in general do not form a complete basis in L2, but if we think about Hermitian functions, Hermite polynomials equipped with Gaussians, we get a basis. So, can I use a decomposition and a mapping on the basis sets and then get like something like a density argument?
What I know is that you can use a frame theory, Gabor frame theory. And this is a very important aspect, and it's then related to the Minkowski sum. It's complicated, but it's feasible. This is something you can really do. And what is strange, or perhaps not so strange, is that Gabor frames play an essential role here for generalizations. But
Is there any other question? I have a comment on the same line as the one before, and in certain as you were, we have considering more or less coherent states.
Yes.
They form a frame.
yes,
So and they are associated to this like ellipsoid.
yes.
So one can use a sort of tomographic idea for any other
Absolutely.
geometrical object.
Yes, yes, there is tomography here. By the way, I forgot to say, this construction of these theorems are actually solve the so-called Pauli reconstruction problem here. You know, finding this wave function or a Gaussian knowing marginals here. And actually this solves this problem here. So there is a tomographic principle hidden behind that, absolutely.
In the sense of that you have a generic geometric object and you can
Yes,
use ellipsoid like a minimal information for reconstructing
yes,
everything.
you're absolutely right. It's that. It's that. I forgot to say that. I should have said that, but okay, time limitations.
Thank you very much for the.
Thank you.
Let's thank again the speaker. And